Hello, hi everyone. Welcome back to CS 700, Computer Science of Continuous Data, Algorithmic Foundations of Numerics. So last time we started talking about complexity of real functions and of operators that map polynomial time computable real functions to polynomial time computable functions, such as, for example, differentiation. So whenever we have a polynomial time computable real function and we have the promise that the derivative exists, is continuous, and has again a polynomial modulus of continuity, then that derivative is again polynomial time computable. And this statement, this theorem is optimal because this additional hypothesis that the derivative must be continuous, that's necessary, as we know from the part about computability, and the strengthening that the derivative must have a polynomial modulus of continuity is also necessary for polynomial time computability of that derivative, because every polynomial time computable function has a polynomial modulus of continuity. So that was about differentiation. And how about the converse? How about integration? What is the computational complexity of integration? And you may have noticed that we did not address that question. A related question is, what is the computational complexity of maximization? In the discrete case, maximization is usually NP complete. For example, integer linear programming is a prototype example of an optimization problem in the discrete setting. Well, it's called integer linear programming. Or even Boolean satisfiability can be considered as a case of a maximization problem in the discrete sense, namely ask whether there exists a value, an assignment that makes a Boolean expression evaluate to true, evaluate to 1 at the maximum, whether the maximum is 1 or not, which is the question whether maximum is 0. So satisfiability is basically maximization where the codomain, the possible values, are either 0 or 1. So all these are classical and NP-complete problems. But gospel or intuition in numerics is that when we're in the continuous setting, then things become easier, right? We have powerful algorithms in the continuous setting, such as bisection. Bisection only works in the continuous case where we have a continuous interval that we can bisect. Or if we often have differentiability, then there's Newton method, right? Newton's tangent method essentially relies on the function under consideration to be even continuously differentiable. But on the other hand, Newton's method guarantees quadratic convergence extremely fast. So the common conception is that in the discrete setting, optimization may be difficult, but in the continuous setting, we have these powerful algorithms that harness, that make use of the continuity, the differentiability to get polynomial time computation. And recall that polynomial time computation is basically what in numerics is called quadratic convergence, linear or quadratic convergence. But also recall that these powerful algorithms have hypotheses. So for example, Newton's method requires having a starting point that is sufficiently close. So the mathematical statement is that Newton's method converges quadratically locally. And what is locally? Locally means must be a point, starting point that is sufficiently close to the final optimum, to the final maximum or minimum argument. And how do we find that starting point? That's actually a pretty involved question. There's famous studies that uh, investigate starting points that guarantee quadratic convergence versus starting points there where there is no convergence at all. I mean, there's a oscillation, or starting points where there is convergence but slow convergence. And classifying these starting points actually easily yields a fractal. So membership to that fractal formalizes the question whether a given point is a good or a mediumly good or a bad starting point. So that says that the question of the starting point could hide some very difficult intricate mathematical questions. And today we're going to resume our rigorous complexity investigations of common operators in mathematics, including maximization, that is optimization, including integration as counter operation to differentiation, including solving ordinary, and including solving partial differential equations. And I cannot stress enough how important that is, right? Being able to prove that a certain algorithm is optimal. That's really the core of computer science, of complexity theory. And that's something that numerics has been missing, has been missed out on behalf of both parties, both numerical scientists, because they didn't have the technology, the techniques, the like NP completeness, and computer scientists have been ignoring the continuous realm of numerics. And all these two things come together today in this lecture. So let me start the slides. And here we are. Right, and the thing we have already started talking about is the computational complexity of parametric maximization. And we emphasize again, we're talking about intrinsic computational complexity. We never talk about the complexity of an algorithm. We may talk about the cost of an algorithm, but complexity is a property of a problem independent of an algorithm. It's the cost of the best possible algorithm. So let's first develop some rigorous algorithms for parametric maximization. And the difference between maximization and parametric maximization is that maximization is a functional. It receives a function as argument and returns one real number, the maximum value of that function on its compact domain. And in this slide, we're going to restrict to the compact domain of the unit interval. So that's ordinary maximization is a functional. Here we consider something more general, namely parametric maximization, which is an operator. It also receives a function as argument, but it returns a function as value, namely the function that given x returns the maximum of the original function up to x. So it's x is kind of a parameter. Maximize the given function on the interval from 0 up to x, and x can vary. And why is this a more general problem? Because if we plug in x equal 1, then that means maximize over the entire interval from 0 to 1. And that's our original functional conception of maximization. So being able to maximize over subintervals, that's kind of a stronger uh, problem. And that we expect that maybe to reflect also in the computational complexity. So let's have a look at the rigorous computational complexity by designing and analyzing some algorithms rigorous in the rigorous sense. So let me point out that we're here in the non-uniform setting where we fix a polynomial time computable function. We're not yet ready in this stage of the lecture to talk about uniform setting of functionals, complexity theory, uniform complexity of theory of functional and operators, because that requires somehow inputting a function. And as we will see later, inputting a function is a delicate endeavor. Finding the right definition for how to input a function is difficult because, in a certain sense, a function is a much larger object information theoretically than a single real number. And we know how to input a single real number, namely by a sequence of approximating dyadic rationals. How to input a function, that's something we were going to discuss in chapter 6 of this lecture. Okay, so in order to avoid that issue, we're going to fix a polynomial time computable function. So it's not input, it's just fixed. What is the input is the parameter of the parametric maximization x. And the first we've observed that computing this new function, right, the parametric maximum, it's a non-decreasing function. This can be done in exponential time, and even more, it can be done in PSPACE. And the algorithm that computes this new function in exponential time and actually in polynomial amount of memory, polynomial in the output precision parameter n, uses the fact that we already know that a polynomial time computable function must have a polynomial modulus of continuity. And we can and will suppose that this or one such polynomial modulus of continuity is known to our algorithm. Since the function is not given as input, but fixed, similarly, a modulus of continuity of that function is not input, but is fixed and is hard-coded in our algorithm that computes the parametric maximum. Namely, that algorithm will kind of virtually subdivide the unit interval. So the goal of the algorithm is to approximate the maximum of the function from on the subinterval from 0 to x up to error 2 to the minus n. So n is a given really input. And to this end, we kind of subdivide the y-axis into pieces, into subintervals of length 2 to the minus n each. Here, 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 and this one here. And we're going to kind of parameterize this y-axis with dyadic rationals of length n, maybe of with numerators, integers c that range from 0 to 2 to the n, because the values of that function range up to 1. So on a grid with step size 2 to the n, that means that the grids, the subintervals, run up to 2 to the n. And similar, we're going to, our algorithm will subdivide the x-axis, the unit interval, into steps of width 2 to the minus mu of n, where mu is a modulus of continuity of the fixed function, which is also fixed, a polynomial modulus of continuity, which is known to our algorithm. And remember, yes, this is a polynomial modulus of continuity, and our algorithm will now evaluate the fixed function on each of these subintervals at some point, midpoint or left point, doesn't really matter. And because mu is a modulus of continuity, that means that within each of these subintervals, the value of the function will vary by no more than 2 to the n. So if we evaluate the function at one endpoint, then we know that throughout the subinterval, the function value will differ from that single evaluation point by no more than 2 to the minus n. That's the definition of modulus of continuity. And by evaluating the function on, let's say, the left endpoint of each of these subintervals, we arrive at, 2 to the mu of n real numbers. That's exponentially, but finitely many real numbers. And taking the maximum of these finitely many real numbers constitutes an approximation to the actual maximum of the continuous function. So this is what happens in numerics all the time. Discretize the problem. The difference or the emphasis here is now that we want a rigorous algorithm, therefore we specify precisely how fine the grid width has to be, and that's exactly what the modulus of continuity captures, namely the grid width. The step size of the x-axis must be 2 to the minus mu of n. That is guaranteed to be sufficient in order for the discretized problem, the function restricted to each of these subintervals to one point in each of these subintervals to be a proper approximation of the original function, and the maximum of all these finitely many values to be a guaranteed proper approximation to the maximum of the original function f. Okay, so that's our algorithm. And since these are 2 to the mu of n subintervals, and evaluating at each subinterval takes polynomial time, because this is a polynomial time computable function by hypothesis, that means the overall running time will be roughly 2 to the mu of n times some polynomial. And since mu of n is polynomial, it's a polynomial time computable function, therefore it has a polynomial modulus of continuity, that is still exponential. Remember that we call 2 to the n squared and 2 to the n cubed, that we call all of these exponential, right? As opposed to, let's say, 2 to the n, which is double exponential. So here the hypothesis really enters that our original function is polynomial time. This hypothesis enters in two places. The first place, that evaluating on each subinterval takes polynomial time. And the second place is that we have an exponential number of subintervals, 2 to the some polynomial in n many subintervals, and not, let's say, 2 to the n subintervals, which would be double exponential. Okay, so that's our exponential time algorithm, and actually that's already a polynomial space algorithm, because each single evaluation takes polynomial time and therefore also only a polynomial amount of memory. Remember, polynomial time also means polynomial amount of memory. And the exponential time part, the repetition for exponentially many subintervals, each of these repetitions can reuse the same amount of memory for storing the maximum value so far. So we don't need an exponential amount of memory, although the running time is exponential, but we can reuse memory. So this is our PSPACE algorithm. And that raises the question whether one can improve that. And indeed, it turns out one can improve that to polynomial time, provided, that's a hypothesis, provided that the millennium problem P versus NP has a positive answer, P is equal to NP, which frankly the majority of complexity theorists believe to not be the case. But the statement says if this is true, then one can actually compute the maximum, the parametric maximum in polynomial time. And Before proving that, let me recall what's the matter about this being a parametric maximum. It means that we need to maximize not in the entire interval, but only on the subinterval up to x, where x is approximated by a dialectic ratio b divided by 2 to the mu of n, where b is an integer numerator. So let's say the maximum should be in this subinterval indicated in gray. And so how can we find the NP algorithm? Well, let me be very clear here. There is no such thing as an NP algorithm. Okay. The statement here says if P is equal to NP, then we can compute that maximum parametric maximum function again in polynomial time. Okay, but you may forgive me for sometimes being less rigorous and say computable in NP, but that is supposed to mean if P is equal to NP, then the algorithm runs in P time. And to prove that, that's an improvement, right? We can basically improve from PSPACE to NP. And to this end, let's recall the definition for a real function to be computable. In time n, it means that we can approximate the function with some dyadic rationals. There's a computable transformation that receives as an argument the numerator of dyadic rational approximation and outputs the numerator of dyadic rational approximations. Right? That's a transformation conception of a real function, and transforming a real function in our setting means transforming approximations to approximation, and more precisely, numerators of dyadic rational approximations transform to numerators of dyadic rational approximations. And more precisely, since we know the modulus of continuity of that function, we know what order dyadic rationals are sufficient and necessary for the argument approximation, and what order dyadic rationals are sufficient and necessary for the value approximation. And the answer is, well, for the argument, we need dyadic rationals of order 2 to the mu of n. So the input to the approximating computation is a numerator to this dyadic rational, and the output is a value, is another numerator. And this is what this function phi n captures, and it depends on n, of course, because that's a precision parameter. So the very definition for a function to be polynomial time computable means that there exists such a transformation on natural numbers, from natural numbers to natural numbers, namely transforming numerators of dyadic rational approximation of this order into numerators of dyadic rational approximation of this order up to this error, where the numerator ranges now from 0 to 2 to the mu of n minus 1. That's the largest possible value because our domain is the unit interval. And now we use that fact. So here we have a classical polynomial time computable function, right? That's from natural numbers to natural numbers. That's the classical setting, not continuous anymore. And to this setting, this is where NP actually applies. We have no real counterpart, at least for so far in this lecture. There's no real counterpart to NP, but the definition of polynomial time computing amounts to some discrete function where P versus NP makes sense. And now we reformulate the maximization problem as a repeated problem which we show to be in NP. And this is the following problem. So the argument to the problem, it's a decision problem, right? All problems in P and NP are decision problems. We're talking about continuous maximization problem. So it's important to identify within that continuous problem a decision problem involving integers, and this is exactly what we have here. So the input is 3 natural numbers. The first is the natural number n, indicating the precision. How precise do we want to approximate the maximum And recall that this precision is input in unary. That means we don't input n, but instead we input 2 to the n, because that means that the length of this number is basically the number itself, n plus 1 actually. So that's the essence of unary encoding. And the other two inputs are given in binary, which makes sense because the third one, C, ranges from 0 to 2 to the n. This is kind of the y discretization. This is the index of the y subinterval we're currently interested in, whereas the second input is a number of the x interval that we're currently interested in, namely how far, that's the last interval up to which we want to integrate parametric maximization. And as you can see, these quantities are all have value exponential in n. Here it's obvious, but here it's also exponential in n because we use a polynomial. Value exponential in n, and therefore binary length polynomial in n, right? So that the binary length of that input is roughly 3 times n. So here the binary length is roughly n. Here the binary length is, okay, to be fair, the binary length of this is mu of n, which is polynomial, and the binary length of this is n. So it's basically 2 times n plus some polynomial in n, which is polynomial in n. So in the sequel, when we talk about length of the input of this discrete problem, it doesn't make much of a difference. It makes at most a polynomial difference between polynomial in n or polynomial in the binary length, because the binary length is 2 times n plus some polynomial in n, which is the same as polynomial in n asymptotically. Okay, now the decision problem, the discrete decision problem that we consider is the following. Given these three numbers, does there exist a witness A of value less than B, such that the discrete function phi n of A exceeds the third argument C? Okay. And why is this a useful decision problem? I will explain in a minute. But for now, let's record that this is a decision problem in NP. Why is this a decision problem in NP? Well, because this witness is obviously has polynomial length. Actually, its value is at most the value of B, one of the inputs given in binary. So that's A immediately serves as a polynomial length witness, and the verifying part is also feasible in polynomial time, because by hypothesis the discrete function phi n, which is fixed because the original real function f is fixed, this function is computable in polynomial time. Okay, let me say that again. The original function f is fixed, and I have explained why this is crucial, because we don't have a way of inputting the function, but because it's fixed, that also means that the discrete approximating function that transforms approximation to approximations, numerators to numerators, is also in polynomial time computable by the very definition of real function being polynomial time computable. And therefore, the verifier part of this NP problem is indeed polynomial time decidable, so that this is an NP problem. Okay. Now, why is this NP problem helpful for our continuous problem, for our continuous maximization problem? The reason is, well, our goal is to approximate the original function on the interval up to b divided by 2 to the mu of n, right? So, and this is exactly our b here. This is what we input, what our algorithm inputs into this decision problem. Let's for a moment, for simplicity, suppose that this NP problem is available via Oracle access, and our algorithm invokes this with parameter 2 to the n. It is supposed to approximate the maximum up to error 2 to the minus n. So it will use this as first parameter. it will use the B as second parameter, B, which is obtained from the approximation to the right interval bound on which is supposed to compute the maximum. And what will it use as third parameter, C? Actually, it will repeatedly invoke the oracle. It will try to repeatedly decide that decision problem for values of C by using a binary search with respect to C. So C is something between 0 and 2 to the n, and 2 to the n and B itself are temporarily fixed. And then our algorithm will search for the largest value C such that this triple belongs to this decision problem. Because by the very definition of the problem, if some C makes this triple belong to the set, then all smaller values of C also satisfy this condition, right? So that this decision problem is monotonous in the third parameter, and our algorithm will use binary search to find the threshold where the largest C which belongs to this, or the least C which just barely does not belong to this set, this decision problem. And under the hypothesis that P is equal to NP, each such checking whether for a given C this triple belongs to the set or not, can be performed in polynomial time. And more uniformly, imagine an algorithm that repeatedly makes an oracle call to this NP problem, or, as I said, under the hypothesis that P is equal to NP, that oracle call can be replaced by an actual polynomial time computation. And as we know, binary search takes a number of iterations. So every query reveals one additional bit of C, starting with the most significant bit, whether C is greater than 2 to the n minus 1 or not, then and so on by section. So that under the hypothesis that this NP problem actually belongs to P, our algorithm can perform bisection to find the largest value C where there exists a witness, an A, somewhere between 0 and B, that is, whether there exists an argument x prime somewhere between 0 and B divided by 2 to the mu of n, where the original function value exceeds that C, because if the original function exceeds C, that means that the function, so if the discrete function phi n exceeds C in value, that's the same as saying that the original continuous function exceeds C divided by 2 to the n in value, right? That's the whole definition. Good, so that's our algorithm, which uses bisection, repeatedly invoking this discrete problem in NP, which by hypothesis is possible in polynomial time, in order to find the least C, such that C divided by 2 to the n is just barely below the maximum, is attained somewhere. And that's exactly the point of computing the maximum, approximating the maximum up there 2 to the minus n. So that concludes our algorithm design and analysis for this parametric maximization problem here. And now we're going to move on to integration. Right. So yeah, before that, let me point out, so we have a PSPACE algorithm, we have an NP algorithm, but the NP algorithm is not really helpful because it depends on the millennium problem, which most people believe to be wrong. So this is not really helpful algorithm. And so the question remains, and we will return to that question, whether our NP algorithm is actually optimal or not. Okay, so but first let's move on to another problem, from maximization to integration. And numerical folklore says that maximization is harder than integration, because for maximization we do have all these algorithms, bisection, Newton's method, and so on. Here we haven't really discussed bisection or Newton's method for the reason that I just pointed out. Um, Bisection is maybe good for finding unique roots, but for finding maxima, I'm not sure how to use that. And Newton's method only finds local optima. That's one constraint, only local, not global maxima or extrema. And second problem is Newton's method requires this good starting point, which is in our setting, at least, I have no idea how to find that. Well, we could guess one, and actually it will turn out later that this may be the best we can do, guessing a starting point as an NP problem. Okay. So numerical folklore says maximization is easier than integration. Our evidence says the opposite. Our evidence will say that maximization is harder than integration. And to understand this again, let's design and analyze algorithms for integration. And again, we're going to look at two versions of the integration problem, more specifically the Riemann integration problem. We're only going to integrate continuous functions on compact domains for now. Okay, and the two versions of integration we're going to look at is indefinite integration and definite integration. So let us recall what is the difference between definite and indefinite integration. Definite integration is where we have fixed lower and upper integration bounds. Let's say integrate from 0 to 1. That's a definite integration problem. That's a definite Riemann integral. As opposed to indefinite integration, where one integral bound, let's say the upper bound, is actually variable. And this is what we're considering here. So the difference is kind of similar to parametric maximization and unparametric maximization. It's also similar in the sense that definite Riemann integration is a functional. It returns one real number, the value of the integral, whereas indefinite integration is an operator. It returns a function, namely a function that returns the definite integral up to the given upper integration bound x, which is given as a parameter. Okay, and on this slide we're looking at indefinite integration at the operator, and on the next slide actually we're going to investigate definite integration. And the algorithm and its analysis begins the same, very similar as the maximization algorithm. Namely, we subdivide both y-axis and x-axis, the y-axis into subintervals of length 2 to the minus n, because that's how precise we want to approximate this time the integral, and the x-axis into intervals of width 2 to the minus mu of n, smaller size, where mu is this polynomial models of continuity. So because that guarantees that on each subinterval, the function value does not vary by more than 2 to the minus n. And since mu is a polynomial, that means the number of subintervals on the x-axis is single exponential in the parameter n. And where the maximization problem, we would evaluate the function all, let's say, left endpoint of these subintervals, and then take the maximum of these real values. Here we're going to take, also evaluate the function on all of these subintervals, left intervals, endpoint, let's say. But this time we're going to add all the areas, the rectangles areas below that evaluation point, right? So that's a typical Riemann sum approximation, right? And Riemann's, the fundamental theorem of analysis says that if the original function is continuous, then it is uniformly continuous, and therefore the Riemann sum converge to the Riemann integral. And how far do they converge? How small do we need the steps of the Riemann sum need to be? Well, this is exactly what the modulus of continuity says. So this is a kind of a quantitative version of the Riemann integral theorem with explicit dependence on the precision parameter 2 to the minus n and explicit dependence on the modulus of continuity of the function. And now the same analysis applies again. This is an exponential time algorithm. This is a polynomial space algorithm. The difference between to the last slide is that now we don't take the maximum, record the maximum over all of these subintervals and blocks up to here, and then continue having a counter run up to the right maximization or integration bound. Instead, we count the number of subintervals because that's what constitutes the area. That's right, the Riemann sum here. And we count all of them up to here and then divide by 2 to the n and 2 to the minus 2 to the mu of n to get an approximation up to the area. And again, although this is exponential here, we can reuse the memory. We only need to store the tentative integral value, the tentative Riemann sum up to here, and reuse the memory for invoking the algorithm that actually returns the approximate function value. So this repeated repetition, this is where we can save and reuse memory to again arrive at the PSPACE algorithm. Now, is this PSPACE algorithm optimal? Well, again, the answer turns out to be negative, but here we need a kind of stronger hypothesis than P versus NP. Here the hypothesis is that if FP is equal to sharp P. So let me briefly remind you and refer you to our chapter 4 on discrete complexity theory recap, that sharp P is the counting class of counting problems, the function problems, counting how many witnesses there are in the discrete setting. And FP is the class of not of decision, but of function problems that can be computed in polynomial time. So here we're quite rigorous. It technically doesn't make sense to compare P to sharp P because P is a class of decision problems, sharp P is a class of function problems, and so they're different for obvious reasons, for trivial reasons. It makes more sense to compare two function complexity classes FP and sharp P, and this is what we do here. And the statement says, if FP is equal to sharp P, then we can actually compute the integral in polynomial time and therefore improve the PSPACE upper bound. And less formally, we're going to say that this is a sharp P algorithm for integration. Riemann indefinite integration is possible in sharp P, but this is only a matter of speech. There's not rigorously such a thing as a sharp P algorithm. Okay, and the proof of the statement, the design and analysis of the sharp P algorithm proceeds by generalizing our previous considerations. So let me recall our previous consideration. Previously, there were 3 arguments to a decision problem, and now we have only 2 arguments to a function problem. So the first 2 arguments are the same as previously. The precision parameter encoded in unary 2 to the n, and the right integration bound, right? More precisely, the numerator. The previous slide, we were asked to compute the maximum up to this point, which is approximated by b to the 2 to the u of n. And now the right integration bound is similarly approximated, but now we need to integrate. On the previous slide, there was a third input to this decision problem, namely C. Does there exist uh, subinterval where the approximating function exceeds the value c. Here, c is part of the witness, namely, we wonder whether there exists a subinterval indexed by a, so a ranges up to b, right? Such that on this subinterval, the function exceeds value c divided by 2 to the n. So that means c is somewhere in the range between 0 and 2 to the n. And whether the function approximately exceeds that value, this is again, as in the previous slide, that's a polynomial time verifiable part. But here now this symbol indicates that we're not interested in whether there exists a witness, but how many witnesses there are. And that's, by its very definition, a prototype problem in this counting complexity class Sharpie. Count how many witnesses are. The witnesses here are pairs of integers that satisfy these conditions. And by the hypothesis here, under this hypothesis, this number of witnesses can be computed in polynomial time. Under this very strong hypothesis, this is a stronger hypothesis than P is equal to NP, as you recall from our complexity picture, because Sharpie is intuitively a larger class. Being able to tell how many witnesses are there entails being able to tell whether there exists a witness, namely by checking whether the number of witnesses is greater than 0 or equal to 0. So that's provides kind of more information. And what I still owe you in this slide about indefinite integration is to convince you that being able to solve this counting problem in polynomial time to find the number of witnesses in time polynomial in n, which is the same as saying time in polynomial in the binary length of the input. This allows us to approximate the indefinite integral up to error 2 to the minus n. And why is that? Well, because let us fix parameter a. Let's say here, this is our a. This is an index to the subinterval we're looking at. And let's count how many c there are such that the approximate function value exceeds c. In this example, there are 1, 2, 3, 4, 5 such values of c, namely the largest value c that achieves that is the value 0, 1, 2, 3, 4, right? So there are 5 such values of c, namely 0, 1, 2, 3, 4, that's 5 values. And that reflects that there are 5 of these boxes that fit under the function value on this subinterval. And that's why the number of witnesses C constitutes a kind of a contribution to the Riemann sum, and doing so not just for counting the number of witnesses C, not just for fixed parameter A, but counting the number of pairs. That's precisely counting the number of these boxes that fit into entirely below the graph of that function. And that's precisely the value of the Riemann sum, right? Scaled, of course, again by the width and height of the subintervals, scaled by 2 to the minus mu of n times 2 to the minus n. So that being able to calculate this immediately constitutes an approximation to the indefinite Riemann integral. Let me emphasize this small but this subtle difference to maximization. For maximization, let me return to that slide. We would need to repeatedly solve this decision problem in NP for bisection, right? For integration, we only need to invoke this discrete counting problem once, and the value returned will be an approximation, guaranteed approximation to the indefinite Riemann integral, well, to the definite Riemann integral up to x, up to error 2 to the minus mu of n plus 1, there's certainly repeatedly where there's a triangle inequality involved, adding various kinds of errors. But basically up to error 2 to the minus n by one invocation of this counting problem, which can be by hypothesis replaced by a polynomial time algorithm. This is where this extremely strong hypothesis enters. So that under stronger hypothesis than maximization, indefinite integration is again polynomial time computable. But we have here a stronger hypothesis, and in both cases the question arises and will be answered maybe today, maybe in the next session of this lecture, whether this is optimal or not. Okay, so that concludes our complexity analysis of our second natural numerical problem. First natural numerical problem is parametric maximization. Second natural numerical problem is indefinite Riemann integration of continuous function. And now we move on to the third numerical problem, that's definite Riemann integration, namely where the upper bound of the integral is fixed and not part of the input. So definite Riemann integration as a functional. So here we fix the upper bound. So we want to calculate the integral over the entire. There's something I should address in both cases. So here we suppose that the function has only positive real numbers, values between 0 and 1. But of course, if a function has also negative possible values, we can kind of add 1 everywhere, calculate the maximum or integral now over this non-negative function in the way I've just described, involving only natural numbers, and then subtract the 1 we've just added everywhere, the maximum or the integral, just kind of undo this horizontal, this vertical shift. Okay. But now, as I've already announced, how about definite Riemann integration? What's the difference between indefinite and definite Riemann integration? Well, definite Riemann integration is a functional. Indefinite Riemann integration is an operator. Definite Riemann integration requires only the function and the error parameter as argument, not the upper integration bound. And since the function is fixed, actually it's just the precision parameter that is part of the input. And the first thing I'd like to point out is that by restricting by moving from indefinite integration, where the upper integral parameter is part of the input, to definite Riemann integration, where the upper integration parameter and of course always the lower as well are fixed, that amounts to different in complexity from classical exponential time, classical PSPACE, classical sharp P, to their unary counterparts, which we introduced at the end of the lecture session 4 on discrete complexity. So once again, the difference is that here, 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 and here, we only restrict to inputs which are integer powers of 2. Okay, so that's kind of amounts to the input natural number being given in the unary coding. Okay, and intuitively that could be easier problems, right? Because we only have integers of certain form as possible arguments, actually very few integers, right? Recall that the integers that are in powers of 2 are kind of very rare among all integers. Okay. And why is that? Well, because there's only one input now. Here we had 2 inputs, the precision parameter n being given in unary in order to make its value coincide with its length, and the upper integration bound given in binary. But moving to definite Riemann integration, there's no need to input the upper integration bound anymore. It's fixed, it's 1, it's hard-coded, and there's only one argument, namely the precision parameter n, still being given in unary, And that's why all of these problems here boil down from regular exponential time and regular p-space to unary exponential time and unary p-space, namely independence on the precision parameter n being given in unary as a form 2 to the n, which we already had seen here already in this tool decision and function problems. Namely now, the strengthening says that this definite Riemann integral is actually computable in sharp P1. And again, let me emphasize that this is only terminology. There's no such thing as a sharp P1 algorithm. It means if sharp P1 is equal to FP1, then this is a polynomial time algorithm. And the algorithm basically is a simple adaptation of our previous slide. And in the previous slide, the counting problem, the discrete problem, would have two arguments, the precision parameter in unary and an approximation to the upper integration bound, the numerator b that encodes the upper integration bound. But now we don't have an upper integration bound anymore. It's hard-coded, it's fixed, and it's 1. So there's only remains a unary precision parameter input, and we ask for all possible pairs of witnesses, not just to those where a is less or equal to b, but to those where a is less or equal to 2 to the mu of n, namely where a can now range over the entire interval, subintervals of this interval. And as I said, this is obviously a counting problem in sharp P1, the universe of sharp P, because the input is restricted to unary inputs. And the number of these witnesses still is an approximation to the Riemann sum, an approximation to the Riemann integral. So the main differences here, now we have only unary discrete inputs, since the upper integration bound, which was previously encoded in binary, is now absent. So that's our complexity of definite integration. But again, the question is that optimal? Right? From practitioner's perspective, none of these algorithms are actually a polynomial time algorithm, nor are they likely, nor is a common conception or belief that this is a polynomial time algorithm, because most people believe that P is different from NP, that FP is different from sharp P, and that FP1 is different from sharp P1. That's the dominant opinion. Well, fair enough, it's only an opinion. There's no proof yet, otherwise the millennium problem would have been solved already. Okay, and we will return to these questions after this slide. This is the final slide about complexity analysis of a numerical problem. Namely, this time we analyze solving ordinary differential equations. So we're going to consider here not a system, but a single ordinary differential equation. We're going to consider an ordinary differential equation of first order only on the unit interval. So here you have your ordinary differential equation. So z is the solution, which is a function to be found, a function depending on time t, and we consider the time ranging from 0 to 1. So we want to calculate the solution to the given, no, actually to the fixed right-hand side, and observe that the right-hand side here now has two arguments, right? First is the time, and the second is the current value of the sought solution to the differential equation z, or z of t, if you like. So and this is reflected by the specification. We're having here polynomial time computable function receiving two arguments. One is the time between 0 and 1, and the other is the value of the solution, which we suppose here to be between -1 and +1. And the output is also, the value is also something between -1 and +1, which makes sense because with the initial condition, remember, every differential equation needs an initial condition with lot of generality. Without loss of generality, we consider the solution, we require the solution to have value 0 at 0. Okay, so this is our generic ordinary differential equation. And for different right-hand sides f, one gets a different actual ordinary differential equations. And an important thing to consider is existence and uniqueness, right? So for when we talked about maximization, we know that the maximum exists and is attained because we have a continuous function in a compact domain. When we previously talked about integration, indefinite or definite, we knew that the integral exists because we talk about continuous function, and that's what Riemann theorem is about. But here, who tells us that this ordinary differential equation actually has a solution when the solution is unique? Whether, well, the fact that it has a solution, this is what is guaranteed by Peano's theorem. So I'm not going to prove that, but refer you to this important statement that because the right-hand side is of the order d is supposed to be continuous. Well, it's actually computable, so we know it's continuous, and that's where Peano's theorem applies. So existence is settled. How about uniqueness? Well, it turns out that under this hypothesis, the solution may not be unique. There may be many solutions. There may be uncountable solutions. There may be a continuous spectrum of solutions with discrete so-called exceptional solutions. And there's a famous construction by Marian Puel and Ian Richards that says, in fact, there's a computable, even polynomial time computable right-hand side, such that there exists a solution according to Peano. There exist many solutions, they're not unique, and none of them are computable. That's a pretty surprising statement, right? There are many solutions, but by a very construction, none of them is computable. It's a sophisticated construction. I'm ready to admit it's an artificial construction, but it clearly delineates the boundary and the insufficiency of our hypothesis that the function f must be just polynomial time computable, nothing else. Then in general, there's no computable solution. Also, I would like to point out the similarity of this theorem of Marian Puel Richards and Marian Puel and Ian Richards. Namely, we had a similar observation where we talked about computing maxima or minima of a function, where also we know that the minimum is attained on a compact interval. Of course, the function is computable and therefore continuous, but in general, there are many minima. The minimum is attained at many points, and remember the construction of Specker of a computable such function, where the minimum is attained at many points, but none of them is computable. The same phenomenon occurs here, just on a higher type. Here we have many solutions which are now functions, not just real arguments. And many functions are solutions, but none of these functions is computable. Okay, so we're talking here about complexity. This is a statement about uncomputability. So I'm going to move on, not delve into the construction any further, but instead let's look how can we strengthen the hypothesis in order for the solution to be unique and also computable at least. Only then can we start asking for its complexity. If there's no computability, it's no point in asking about complexity. So this is from 1971, a statement from Puel and Richards. And the strengthening that guarantees uniqueness is Lipschitz continuity. And here we're going to consider both Lipschitz continuity and strengthening of Lipschitz continuity, namely continuous differentiability, which you recall implies Lipschitz continuity. Okay, so right. So let's suppose the function is still polynomial time computable, but continuously differentiable. Then the solution is unique. That's the Picard-Lindelof theorem. Even the solution is Lipschitz suffices to guarantee uniqueness, and actually the solution is computable, and a common method for computing the solution commonly employed in numerics is the Euler's method. Euler's method approximates the derivative with a finite difference. Remember, we talked about divided difference, finite difference, when we talked about computability of derivative of analytic function. And in solving differential equation, replace this differential equation by the following difference equation. So suppose we have already calculated an approximation to the solution at time t, and now we want to calculate the solution at the next time step t plus delta, where delta is a small constant, and how small, this is something we're going to discuss in a minute. But for let's now observe that replacing this difference derivative with a difference, divided difference, z of t plus delta minus z of t divided by delta. And that's an approximation to the derivative at z of t. And doing some algebraic manipulation gives rise to this, that this is an approximation to this quantity. And now for this, we can apply the right-hand side. So replacing the derivative z point of t with f of z comma t. So now this is this time stepping method, calculating the derivative of z at incremental time step from t to t plus delta, knowing using our previously calculated approximation to z at time t plus delta, this small constant, times, or as a weight to the right-hand side, the driving force. So that this is kind of an iteration equation, right? Knowing the solution at time t, we can compute from this an approximation to the solution at time t plus delta. This is Euler's method. And let me emphasize that although numerics has devised much more advanced methods, higher order methods, Runge-Kutta method, but actually their complexities turns out to be almost the same on the rigorous perspective. Namely, so how large should we choose our parameter delta? Well, this is where the models of continuity of the derivative here enters, right? So our function f should have a polynomial modulus of continuity of its derivative, and so we use that modulus of continuity plus some polynomial slack, and this is the step size that is sufficient to guarantee that this iteration, that all the errors we make in each time step, right? There's an approximation error in each time step, and this magnitude of the parameter delta guarantees not only that each single approximation makes only an error which is polynomial in n, but also over the course of all these approximations, the accumulated propagated error, right? So every error we make at one step propagates through all subsequent steps, and this all has to be taken into account in the error analysis. But the baseline is if we choose this, which is something polynomial, 2 to the minus some polynomial in n, then after reaching the final time t equals 1, then we're still within polynomial error 2 to the minus n. And well, this of course means that we need to make exponentially many time steps, right? If the single time step has length 2 to the minus some polynomial in n, then we need to make 2 to the plus some polynomial in n many time steps of this math width through a climb from initial time 0, where we know where we're given the solutions value, up to the final time t equals 1. So this is an exponential time algorithm, but we can again improve that to a PSPACE algorithm, polynomial space, because we only need to store the approximation at each of these time steps. We don't need to store all approximation at all previous time steps, right? Only the last previous time step gets involved, not all previous. So it's kind of like mathematical induction versus strong induction. So here we have basically mathematical induction, and this turns this into a PSPACE algorithm. And the question again is, can we do better? And the answer is, we don't know and probably not. And recall that this is different from integration. Let us recall this, our complexity estimate, our upper bound of Riemann integration to our complexity estimate of solving ODEs. Riemann integration is a special case of solving ODEs, right? So in the Riemann integration, we're given a right-hand side function f, which does not depend on z, just a function of one parameter t, and we're looking for an antiderivative. We're looking for function z, whose derivative is f. So that Riemann integration, indefinite Riemann integration, is a particular case of solving an ordinary differential equation where the right-hand side function does not depend on z. And since this is a special case, since solving ordinary differential equation is a priori more general, therefore also its complexity we can expect to be possibly strictly larger, but still definitely at least as large as the intrinsic complexity of Riemann integration. And this is exactly what we observe here, right? So for Riemann integration, we got away with a complexity class sharp P, which, as you know, from the complexity picture, is a subclass, conjectured a proper subclass of the complexity class PSPACE, where again, now you allow me to secretly identify decision and function problems, because FP space and P space are basically capture similar complexities. So to summarize, we have rigorously analyzed the computational complexity of 4 common numerical problems. Well, actually 5, but the first was differentiation, where we obtained that polynomial time differentiation basically maps polynomial time computable functions to polynomial time computable functions under the necessary hypothesis about the modulus of continuity of the derivative. For integration, we saw, which is the kind of converse to differentiation, we got a complexity estimate of sharp P. We designed the sharp P algorithm in a rigorous sense. More precisely, if P is equal to sharp P, if FP is equal to sharp P, counting problem, then we get a polynomial time algorithm, but this is a pretty strong hypothesis. For indefinite Riemann integration, for definite Riemann integration, we could get away with this smaller class, probably of sharp P1. Well, we didn't really use this smaller class, but the hypothesis was subtly different. The hypothesis was that FP1 is equal to sharp P1, right? And this question is not known related to whether FP is equal to sharp P, FP is equal to sharp P, and FP1 equal to sharp P1. I'm not aware of connections between both. Well, if fp1 is equal to sharp p1, then fx is equal to sharp x, but I haven't really introduced these complexity classes, so let me chip over that. And our uh, fourth numerical problem was maximization, which we saw computable polynomial time, provided that P is equal to NP, decision problems. And finally, we talked about the complexity of solving ordinary differential equations under this additional stronger hypothesis that the right-hand side must be continuously differentiable, which is important to guarantee uniqueness. And here we saw that we analyzed Euler's method and pointed out that it can be computed in P-space, and all the other methods, Runge-Kunger methods, also, if you look at them, are basically P-space algorithms, because they also require use these exponentially small step sizes. There are some factors here. Well, numerical people say Runge-Kutta is of course faster, and it is, but it's only faster by a polynomial factor, which does not put it lower in the complexity class P space. Accelerating by polynomial factors still remains within the complexity P space and cannot get us down from P space to, let's say, sharp P, NP, or even P. Okay, so time is up for today. Next time, we're going to briefly recall all these complexity estimates and address the important question of whether these and which of these are actually optimal. And this is, as I keep emphasizing, something entirely new. Nobody in numerics has the techniques to prove optimality of this algorithm. Actually, when I tell this analysis to people in numerics, they tend to be pretty surprised um, about this, how these classical complexity classes NP, sharp P, and P space enter in the analysis. And next time we're talking about optimality of these complexity classes. So that's all for this time. Thanks for listening. Thanks for your interest. And see you next time. Goodbye.